Okay, got everybody's attention? Yeah, I'll close the door as we get started. Today, we're going to have our speaker. This is Dr. Tarditi. For those of you who were here last week, you remember he gave a talk sort of last minute to fill in last minute issue that we had. And so today he's going to be giving the talk we really intended to do. And so, if you don't know him, Dr. Tarditi, he's a research faculty member here at UHCL, and he has been working with some of the graduate students and undergraduates doing research here on campus. Before that, he was an adjunct for the past several years. So this summer, he's also going to be teaching a course on research topics in plasma physics. So I'm going to. Yeah, which is going to be elective offered during the summer. So with that, I'll turn it over to Dr. Tarditi.
Okay. Well, welcome back for the people that were here last time. And I won't repeat myself. At least most of the topics will not. This is about applications of plasma physics. Since we're in the physics department, to say perhaps plasma science, because it's work engineers. Applications to aerospace technology. So usually plasmas and aerospace and common knowledge are not necessarily related. And I'm going to show you that for new technologies, really what we want to do. Let me just get into the rationale of this. We have a work. Okay. The aerospace sector is going through a rethinking of its own roles and goals, perhaps, and you hear about these buzzwords all the time: game-changing technology. What I'm going to be talking about here are some technologies that are actually can be representing game-change technology, not to this point, okay, not just getting this UFO or, but something that maybe gets a little closer. We have several low-hanging fruit because there seem to be fairly easy to reach in terms of early development. Something that's been really underdeveloped. When you start working on it, you make a lot of progress right away. And then as soon as you can get, a little more closer to application, then of course it requires more funding. But you got to do the homework anyway, right? So if you never start, you won't ever get there. And the other point is that plasma science is intrinsically very interdisciplinary. So it's a perfect excuse to get engineer, physicists, and computer scientists, indeed, working together. Now, as far as we are concerned, UHCL, we're trying to maybe build a little more momentum in the collaboration with the local aerospace realities, which are mainly NASA and satellite companies. And we also have a collaboration with a major aerospace engineering department, which is being engineering and we being physics. It shows that we're implementing exactly what I said in the previous slide. We're trying to kind of join forces to get some projects off the ground. The purpose of this talk is basically to stimulate interest, whether it's somebody from NASA or from the university, to create a connection and through students and the workforce that works on NASA already. Well, we are in a sort of impasse, and everybody is saying, well, we can't do anything because we got no money. So how are we going to get out of this? There is something that can be done with little. It's just a matter of striking an agreement with somebody else that's already working on it and moving on. Another obstacle that we face several times is that is management will not jump into something new that you're going to propose just because it looks good. Okay, You can say what you want, but you're not going to convince somebody who's been not working on, say, advanced propulsion, never had before, to put money and time and people into this new endeavor, even if it looks good and looks required and necessary. You have to, build credibility. You have to have somebody else that they can rely upon, make them feel comfortable. That's when, with your partnership with universities and, for example, NASA, JC, these problems, part of the problems can be solved. Now, these are the steps that the next endeavors are for space exploration. I'm talking about aerospace. It's not just space, but there's a lot can be done, for air transportation, obviously. We're facing, the typical segment to get somewhere and come back, right? Life in orbit could be perhaps skipped, but it's part of the NASA current plans to keep the station for another 10, maybe more years up there. And then long distance travel. How are you gonna assess all these issues? The real problems are these. Okay, the heavy lift is just a matter of money, and life in orbit. Well, that's a picture of space junk. That it's calculated trajectory of objects. Actually not they're above the radar cross section, so you have to see them. The life in orbit requires, for long term, the present, requires some more careful strategies as far as protecting our assets up there. This is true not just for the ISS, but for the French shuttle, for example. We are not necessarily in the know for that. Long distance travel, the space radiation is the main enemy. That picture I wanted to show you that when the spaceship leaves the magnetosphere around the Earth, things are going to get much worse, okay? Because we're not in this kind of cozy environment we are right now. All the radiation we can get, we'll get. And sometimes the sun is misbehaving, so it's going to get even worse. Re-entry is another critical phase, not just for landing back on Earth, but you're talking about going to Mars, and you can use the atmosphere on Mars for aero capture. But you have to design things properly. You can save a lot of fuel if you do things right. You can control your descent carefully. That obviously is the Apollo when there was fish out of the water. You can see the damage of the heat. Of course, it was designed to survive it. The main problem with the Apollo re-entry in general with capsules as opposed to shuttles, which we're not using anymore, is that once you got your trajectory, that's it. You better do it right at the beginning, because there's virtually no way to control things. And so what I'm going to talk about, some technology that allow you to steer essentially the spacecraft while it's coming down. All right, so what do we need? We need new design. Okay, this gentleman a little while ago came out with creative ideas, and that's how we made it the moon. Now, can we match his ideas? Can we do something at least gets close to that? Okay. Okay, since we were talking about plasma physics applications, I will briefly touch on what is the plasma. Most people probably know. I'm going to make it a little simple, straightforward. So just let's say the plasma is what used to be at the beginning, and it's something like an ionized gas, but a little different, right? I'll try to summarize the main point here. It's more of an academic decision, if you like, but it has some engineering consequences. So the full state of the matter, on the bottom, lots of the plasma and the familiar plasma ball that everybody knows. So it's a gas, it's ionized gas, but when you have a distribution of particles that are almost uniform everywhere and do not allow for strong fluctuation of charge. And you have a lot of particles, so just enough, as many as you need to avoid to produce some collective motions where the particles kind of moving all together as opposed to single particle trajectory going around. That behaves like a plasma. So you can actually have waves and some plasma confinement. Those are the things that we use to manipulate plasmas to create the technology that we want. Plasmas are everywhere, as you've probably seen this picture already too many times, but the point is that the temperature and the density are the main parameters are spanning to a very large range. And of course, on Earth, we're mainly concerned about cold plasmas on space, on the stars. The plasma is much more energetic. Around the Earth, for example, the ISS is floating through an ionospheric plasma, which is very tenuous, yet it can cause a lot of damage because the energy of the particles. Okay, so this is enough for plasma physics for today. These are the some of the applications that I want to touch on. Maybe there's something else, but these are perhaps the most appealing. And they fit kind of the picture of the journey that I said before. You know, that they take off, heavy lift, life in orbit, long trip somewhere, exploration. If you get there, to land, come back. Maybe let's start to see what's happening with the launch situation. So you're on the ramp and you can get lightning. Okay, you're flying, it's an aircraft, you can get lightning. You can see those are events that are necessarily happen all the time, but you really don't want to be in the aircraft when that happens. That was happening in Japan. Well, you can see that. What's the point here? The point is that right now we're going towards composite design for aerospace, mainly aircraft as well, but aircraft and spacecraft. So the conventional technology that is basically making a missile that is made of a metal tube is not going to be there anymore, and we're going to be exposed to lightning. And the avionics inside the aircraft or spacecraft will be exposed to lightning effects. So, so this is a picture of the Ares 1X, and you know this could be the scenario. Okay, you're going up there and you get a strike. Why is that happening? Well, you're not launching in a storm, right? I mean, you're not crazy. Well, what happens is that if it's an electric field in the atmosphere, especially in the upper levels, is high enough, you can trigger a lightning, and because you stick a piece of metal into the atmosphere, you distort the field lines, and that's the kind of mechanism why you get lightning. Now, if you launch something that does not have enough metal, it won't be certainly metal free. You can't make a rubber metal free or composite. Suppose the composite would be a shell around. Okay, you still have metal, so you still have that effect. But the point is that if you don't have a metal shell, the lightning is going to hit you, and you're not sure what's going to happen next. So one application that you can tap from is a plasma modeling for studying a lightning plasma, and this is an example of what kind of simple modeling you can do with a plasma discharge already set up. And you have a sort of sketch rocket, and you can look at what's happening with the electric and magnetic fields while the discharge is running. You can do something more, which has been done in the past. That this is a sketch of a lightning discharge that hits in this piece of metal here, and this lightning discharge is moving with the velocity v right here. So we can actually simulate as the lightning discharge sweeps through the rocket, because when the rocket goes up, partially you have a velocity, a relative velocity between the rocket and the discharge, essentially, in the cloud. And so you have this phenomenon where the lightning hits you here, and then the plasma flies through, and it may hit different points. So you can calculate what are the most probable locations for lightning strike, but you don't really know what's going to happen next. So you're going to be very conservative and say, okay, well, let's put metal everywhere and make this rocket really heavy. Okay, so I'm going to be safe. But this approach is not going to fly. Okay, so you have to do the smart way. Okay, trying to figure out, okay, well, these are the critical areas. We're going to protect these, and then that's it. All right. So this is what we can do with lightning plasma modeling. Now we want to go up, right? We were here on the ramp taking off. Another issue is okay. Let me have it. Okay, I'm going to do manually. It's not working. Another issue is to how to take off and send a heavy load in orbit. Okay. So, okay, well, we know how to do it. We went to the moon, so obviously we know how to do that. But the point is, it's expensive. Is there a better way to spend a pound in orbit and pay a lot of money? These studies have been done for quite a while. Started in Russia and with applications for hypersonic aircraft. There were some aircraft concept that was supposed to go at Mach 7, 8, or even 10 and beyond. Well, what happens is that at that speed, the scramjet, the supersonic combustion jet engine doesn't work very well. So the efficiency is lost. So, well, you can stick to a rocket, and then the problem is the rocket you have to carry both oxygen and liquid hydrogen. If you're using liquid hydrogen, you have to carry the oxidizer with you. You can't take advantage of the air anymore. So you want to still take advantage of the air and burning fuel using the oxygen of the air as much as you can before switching to a rocket. But if you're going that fast, the efficiency goes down. So what we're trying to do, this idea is to take the air that comes in, make it going through an MHD generator, which I'll show you what it is. It's something that produces electricity, and it slows down the air a little bit. And then we go through the regular jet engine and get it exhausted out. In this process of exhausting out, this gas will be ionized. And so you're using the electric energy that we produced before to give an extra kick to this gas. So although overall the energy that you're using will be not, we're always losing some energy, obviously, in this MHD generator, MHD accelerator process. The gain that you're getting is here, okay, with this optimized scramjet, which the efficiency goes quite much higher. So the idea is that there are two simple concepts. One is called MHD generator, the other is called MHD accelerator, okay? The generator is something that you're making a box, okay, with a hole, okay, a pipe, basically, all right? You're just sending air through, but this has to be conductive, okay? So it's a plasma, it's an ionized gas, okay? Enter this way and come in the other way. If there's a magnetic field that crosses this way, and these two orange things are electrodes, are metal things, you can actually draw current. You can turn on the light, okay? Using the kinetic energy of this ionized gas that goes through, and because the effect of the magnetic field, you're collecting charges on the electrodes, and you can run electricity to it. Well, so you can charge the battery anywhere you want. So you can take that would be the intake of the supersonic or hypersonic craft, and then you're producing energy. All right, and you're slowing down the flow. Okay. All right. Then when it comes down to the end, the other side, you can do the opposite. Okay. If you are going to provide electricity between these two electrodes, and you still have your good magnetic field, then the working fluid, which is still ionized gas, gets a kick. Right. This is called MHD acceleration. So you can play this game. Of course, you're going to have losses, right? So if you producing energy on one end and then you put it back on the other, you're going to lose something. What I said before, the whole game works because the scramjet efficiency goes up drastically at Mach 10 or even beyond. Okay. All right. So that's what they're planning to do. These are one of the many, concept designs of aircraft that fly at Mach 10 or above. And so you look at this, the bottom here, okay, which is sketching the bottom of this aircraft where the air comes in and then it gets kicked out. So several studies among this one very recently. So this stuff is actually very recent stuff. It started a long time ago, but it gets, it gets worked on at very low level. But, so the idea is that, again, you have an MHD generator here, then compressors, turbine, that's conventional aircraft stuff, and then an MHD accelerator and a nozzle. And these are actually the pieces or the working pieces that have been used to do this study that are real things, okay? And so you can calculate how the system will be efficient and, give a lot of engineering. That's great. All the different pieces have to work, obviously. The more efficient you are, the better. This has been done in Marshall, the NASA Marshall Space Center, funded by the Air Force with other collaborators. This is just to see how this MHD generation process works. Okay, so this plasma, this air comes in and becomes a plasma, and then it gets through this MHD generator and it gets out. Okay, so this is a sketch of this device. The air comes through here. There's a magnetic field here. This is the coil, and this is the last part, the exhaust. Okay, these are the actual real pieces. Okay, this picture here, the sequence, and it shows you the effect. Okay, so here, this picture is we're turning on. Then the scramjet, the actual rocket, the jet engine is start working. You see the little, flare here. Now, when we turn this into a plasma, you see a big difference, right? So this thing really gets a big kick, all right? So it's been tested. It does work indeed. Similar experiments but the different arrangements have been done still in Marshall for the actual purpose of propulsion. This thing here is particularly interesting for us because here because this could be easily, but let's say without spending millions of dollars, which in this case makes it easy. It should be done in the object adjacent. Okay, we have a beautiful device there, a 10 megawatt thing. Sometimes gets really busy when they study the re-entry effect on tiles, for example. Now the shell passes aren't using anymore. There was some kind of Orion work. Now, so they didn't do that. But the point is that this machine is there, and it's proven it's really strong jet and hot air and plasma, and they have a big chamber. You can do a lot of stuff. Okay, that's what I was talking before. The right connection, a little bit of seed money, maybe not even that. Just getting maybe two students are interested in do some work with JSC and a partnership between NASA and UHCL. These kind of studies can be implemented with some very interesting, appealing, at least perspective results. All right, well, this was not the automatic way, so I have to get out of this. All right, Okay, so the point of this was we can improve the conventional rocket propulsion with plasma dynamic systems, essentially, magnetodynamic efficiency. Now we're getting to orbit, and we are maybe stay on the ISS. We want to go somewhere. We need a rocket to go somewhere from orbit to see a planet. The electric propulsion is the way to go if you want to go somewhere. Okay. The way we made it to the moon is just too expensive for going to other planets, and I mean you can still do it. It's just building very, very heavy rockets and sending everything to orbit and stuff like that. So you probably heard this before. Especially here in Houston, we've been trained a little bit because the activity of the former Advanced Space Propulsion Laboratory at JSC about this need of electric propulsion. The business it boils down to this equation. It's called the rocket equation. It simply says, well, if the exhaust velocity of your rocket gets larger, the delta M, which is a fraction of mass that you need to eject, it gets smaller. All right, that means you need to have for a certain delta V, for a certain acceleration that you want to have, you need to carry less fuel with you, okay? So if you're able to somewhat throw this fuel out of the rocket faster, you need less fuel. That's the whole trick of electric propulsion. We're using faster ejection and less mass. So the trade-off is the more energy you have available on board, the less propellant you need to carry with you. And if you have time to do, a trip, then you don't need that much power, of course, obviously. But the point is that you got to have an electric power on board, okay? Beefy electric power at some point becomes beefy. Okay, there is a lot of there are a lot of ideas, a lot of thinking has been done on electric propulsion concept. I'm gonna just glance through some that you might have heard. Some, of course, you heard, some less heard. The first one is the ion engine. Is the first one that really was sent into space, and it just accelerates some ions to a grid, a little bit like the cathode ray tube, except that you're accelerating ions and not electrons here, but it's an electrostatic accelerator. This is Deep Space One, the little probe that went that far out of the solar system with the ion engine. You probably heard about the Hall thruster, which is based on this phenomenon that again you got to cross similar to what we discussed, the same physics that we described before. I got a current going through this piece of metal, and magnetic field is perpendicular. You can collect an electric field or potential across. Okay, you're using this physics to confine the electrons more efficiently in these ion thrusters, and so you're gaining an efficiency. The whole thruster has been built in different countries, and it's been used quite a bit. That's the way it looks like. Okay. Note that we have fairly small thrust with this example. So these are the specific impulse 1,000 to 2,800. Okay. So it's not super high, the specific impulse, and it's got a decent kilogram per kilowatt factor. They build all kind of shape and size. So this is you're probably very familiar with is the Vasimir that was developed at JSC, and now is the proprietary project of the Adastra Corporation here in Houston. Some concept that was originated by the inventor of the Helicon source, which is at the kind of core of all these plasma thrusters, is this double layer. It's an experiment that they've done in Australia. This is a view of the plasma in the chamber. Essentially, it's creating some kind of a wave oscillation and accelerates this plasma because a potential difference between inside the plasma itself. Another experiment was done in Princeton. Again, it's based on the Helicon discharge. So all these experiments that I just mentioned are using radio frequency, and they do not touch the plasma. This is what we're trying to stay out of electrons. Okay, we don't want to have a strong current going through these metals. This seems to be the most appealing thing, especially if you're looking at the long-term application for a spacecraft that takes 2-3 years to travel somewhere. You don't want to have a strong current going through an electrode and suffering erosion. Another experiment was done in Marshall, University of Alabama, in collaboration. In this case, they were accelerating little blobs of plasma through a magnetic field, essentially. The application of electric propulsion are not just long-term interplanetary mission. Obviously, the commercial sector is already using them. It's using full thrusters to keep satellites in orbit. You don't want to lose the precious assets after 2 years when they run out of fuel. And of course, there are defense applications as well. I talked last time about this. I also would like to mention that the cost of keeping assets in orbit is not negligible, and this estimate was done a few years ago, so maybe the number is not really right, but maybe it's a little more, but it's still a lot of millions of dollars a year just to keep the ISS in orbit, because you have to just lift fuel and send it up to just give them a boost. Now, one thing I want to mention here is the long-term perspective. Okay, this is what I talked last time, so I don't want to spend too much time. But one thing is to be considered. This is the best you can do in terms of designing a rocket. Okay, for those who were not here last time, you have a fusion reactor that produces plasma jet, and then you focusing plasma jet, massaging a little bit to a magnetic nozzle and get your exhaust, and you go. All right. Well, it's not that simple. It's in fact much more complicated. But if you have this in mind, for those that were on you last time, you can design a mission, and you will be probably the closest to the optimal mission you could possibly ever have. Okay. If you know how much this thing weighs and how much power you have to have on board to make it work, you have the best mission to go to Mars and Jupiter with the next star. So then you go down from there. That's kind of defining your kind of upper limit or boundary. Okay. Okay. We're doing time. How are we doing time? Okay. So time to. All right. Another thing that is interesting is, and this, what we're doing when we go somewhere, right? Well, we just walk around and explore. This is what happens on the moon. Okay, on the moon, there's no atmosphere, and you got a lot of dust everywhere. Okay, the fact that you have no atmosphere means that the dust particles don't stick to each other. What you have on the moon, right close to the surface, for all intents and purposes, is a dusty plasma, which is not a word that or a term I created right now. The people that are actually working on dusty plasma, you can find them in the literature. They're plasmas that are not made of ions and electrons, but they're made of little grains that are electrically charged, and they seem like ions, but they're a lot more massive. And so you study the physics of dusty plasma the same way you study the physics of plasma, just scaling masses and a few other things. So if you are thinking about long-term exploration of the moon with human establishment and little cars that go back and forth and humans that roam around, at some point you're going to have a problem with the dust. The dust is going to get everywhere. It's going to get into your gear. There are issues that are related to reliability of your equipment. There are ways to protect from some of the least impact of the gear of the dust on the gear using electromagnetic field, taking advantage of the fact that this dust is electrically charged. And so you're using plasma physics to control this flow and study way to avoid it. Well, I'm not going to go into detail. Another thing that I like to mention is something can be used in takeoff, on re-entry, on aircraft, supersonic, hypersonic aircraft transfer, on after aerocapture on Mars, for example, any celestial body that has an atmosphere where you want to use the atmosphere to slow down as opposed to using rockets, which of course saves fuel. So you got to control your descent, your trajectory. Well, there's simple ways of having an aileron, like a good old airplane, and just moves and changes the flow. This example was an experiment was done back then. You see the little purple glow on the right side of the picture. It's purple there, yeah. That's actually plasma discharge that occurs on the surface of the wing. Okay, so it's a profile of the wing, and you see the attachment of the flow is drastic. Anybody has an aerospace engineering background, say, "Wow, this is great," because this is really the dream of an aerospace engineer to have this kind of airflow attached to the wing, and instead of all the turbulence and the sort of a shock occur. So the fact that you have a plasma there will control the airflow, okay, and allows to control the aircraft essentially. The experiments have been done in Russia using a wind tunnel followed by an MHD accelerator, which is essentially the purpose of this is giving a really fast speed to the wind tunnel that you cannot achieve with conventional methods. And so you're essentially simulating a supersonic or even hypersonic airflow. And then once you get through this nozzle and into a chamber, you can put a wing-like device or anything like that and study what happens with this flow when it hits the wing. Well, inside the wing, there's a magnetic system, coils, simple coils. And so you can study what happens if you put a magnetic field with this ionized flow. This is similar to what you're getting in a reentry phase when your craft is coming down. You have a really strong friction between the craft and the air, and that produces a lot of heat, which produces some ionization. You can have a famous plasma around your craft, and that's just enough to block your communication, as you well know. You can use that plasma to your advantage and having a magnetic field on board to control how the plasma goes around the craft with two purposes. One is to basically shield the heat, to deflect the heat from the actual surface to a flow that goes around. So your heat protection requirement will be drastically reduced. And secondly, if you have a system on board that collects electricity on surface electrodes on the actual fuselage, you can draw a current for the MHD generator effect that I explained before. And if you use this current on board, you're essentially slowing down the aircraft or the spacecraft because you're using the energy, the kinetic energy of the falling aircraft, the spacecraft, okay, to your own advantage. And so you're losing essentially kinetic energy. And in a sense, you're creating a parachute effect. This has been studied. These are the electrodes on the surface of, on a leading edge of some airfoil or whatever surface is exposed to this airflow. And inside there is a magnetic field. Okay, so you have really the electrodes are right on the surface. They're not gonna stick out and produce any resistance. This is an actual experiment done in Russia. And interesting enough, this is another thing I was going to touch. This experiment could also be done very easily. And I talked to people there to be a little excited. All you have to do is just put a little coil behind one of these piles that they're using already for the session. And running, I don't know, 2 cents an amp, maybe 100 amps, low voltage, perfectly safe. You can gain a lot of physics. These are experiments that don't cost anything really, and you can gain a lot of physics, a lot of data because we already have the device there. I mean, it's sitting there literally. It's an idea that I've been working on a little bit, where you can create a plasma flow inside a wing, or any part of the aircraft where you duck in the air, like with hypersonic concepts. They always have an air intake somewhere, because they have to have the air to feed to the engine, obviously. So if you put a coil around this duct and you're ionizing this air, which you can do, okay, you do it in the lab. You can sprinkle some electrons to make it even easier, or you can speed the air. There are different ways. You turn the air flow into a plasma, basically. Then you have a plasma that goes through the duct, and you can control this plasma with a magnetic field. What you need is a fraction of a degree of tangential deflection to create a force that will control the aircraft. And you can do this in real time with a kind of electronic loop system. So you have essentially an autopilot that acts on a 1 microsecond time constant instead of a millisecond on a mechanical system. All right, I think it's about time to close to wrapping up here. Okay, so I've been touching on some of these examples of what can be done with. The whole point of this talk was just to maybe get people excited about collaboration and starting some, students can come to the university and do a master thesis or a PhD work and working in collaboration with NASA or aerospace companies, for example. So this MHD augmentation is what I mentioned before. That could be done with the current hardware we have here in Houston. We can do a lot of for little, basically. Just made some assessment. This is what NASA likes a lot. The technology readiness level. It's a DoD thing that was borrowed by NASA, changing a little bit. And so, this is where this would fit. It's a technology development. It's not a basic research. It's got some real engineering, interesting applications, and it's a timely. Okay, it's something that people need right now for heavy lift. All right. So other examples are, of course, what we're doing for the nozzle and for electric propulsion. This is something that actually been currently going on at UHCL. We've have a little grant, and some work has been held. It's actually going on right now. The magnetic nozzle, as you probably know, is some kind of diverging magnetic field that looks like this. Okay, and so the flow goes through and gets ejected. How that gets ejected is a little different than a conventional rocket nozzle. For example, you can see the plasma being turned into some little structure like this, or a little more complicated. But we're trying to figure out how this nozzle works, and we're doing it computationally. Okay. As a code has been written and used originally for magnetic fusion energy application, but has been adapted a little bit, and we can study how the magnetic nozzle, which is the critical element for plasma propulsion, whether you want to use any of those electric propulsion systems I mentioned before, you end up ejecting a plasma somewhere at the end. You want to study all these things. You want to make sure the efficiency is great. Okay, the better, the higher the efficiency, the better. So we're looking at what happens for the plasma. We want to make sure that it leaves the rocket. Without getting into the detail, show some example. Okay, this is an example of a plasma flow that goes through a magnetic field, and you can see that this should work now. Yeah, okay. So you see the black field lines, the black lines are the field lines, the magnetic field lines in the plasma, and it goes through, it kind of distorts the field lines, almost like rubber band. So this is maybe maybe 100 microseconds worth of life in this plasma that goes through the magnetic field. Okay, in this particular case, the simulation was a bounded simulation. So, like you have a plasma tank, like an experiment here on Earth, and then you see what happens. Okay, you can also look at something that is the space application version of that. And you see that basically the flow goes through and leaves the system. And so you're really interested in what happens closer to the injection, not too far away, because then you have to have a huge model and a lot of computer time. But for designing a plasma rocket, you need to understand how this magnetic nozzle works. And if you look at the field lines, these are a high definition picture of the field lines, and I'm not showing the movie, I'm just showing you the structure that are forming. That's what happens, okay, when you have this magnetic nozzle and the plasma goes through it. There are some other things that I'm not going to go into detail. You can study using plasma effects, what happens on the surface of the ISS, monitoring it, and make sure that it doesn't get ruined by bombardment with MHD, means, as you know, micrometeors and orbital debris. Some you can see on the radar, but some we can't, and you only find out when it's too late. And maybe throw holes on the surface. Eventually, it can cause damage, obviously. So there are ways to diagnose that as well. I think I touched most of the topic, except one I'm going to mention for those who are computer science inclined. The simulation it plays a critical part now in aerospace. And if you're familiar with physics and plasma simulations, you know there are a lot of codes around there. All these words may not mean much to you, but the point here is not that. The point is that there are a lot of different codes that are available, and each one is simulating a specific aspect of the physics. Now, if you try to put them all together, you get an integrated modeling. That's a computer science project, okay? You don't even have to know much about the physics, okay? These are black boxes. They're giving data in and out, okay? So you can just do that and not even be aware of what the plasma is like. And that's what I was saying. You can bring computer science and physicists and engineers together in doing this kind of thing. This is not simple, okay? I mean, this is just a PowerPoint engineering, obviously. Behind this is a lot of stuff. It essentially boils down to making computer codes talking to each other as they run, okay, in real time, so which are, it can be done in different ways. And if you have one single code, that runs one particular problem, you study a physical phenomenon, okay? If you have many codes that are talking to each other, you can go from a complex physical system to an actual engineering application. And that's what you need, all right? Because most of the time now we're interested in a design which gives us a product that works the first time. We don't want to go back to the lab and changing things. The system and the design are very complex. All right, so I think I can stop here, and these are some of the interest research topics that we have here, and relating students, future students, current students, into maybe some graduate work. Happy to take any questions.
Question?
Sure.
On your first diagram, you have a picture of the sun in the lower middle.
The first diagram.
Solar radiation never really discussed.
Yeah. The solar radiation is something that enters in the magnetosphere, when you're inside the magnetosphere, like the ISS activity, for example, as well as protection outside. The solar radiation, as much as radiation comes from cosmos, is protons, mainly energetic protons. There are some ways that you can, besides building heavy shields, okay, I'm not talking about all. There are some ways you can design spacecraft for a long trip that can be shielded by radiation. One is a passive way, having hydrogen-rich material, which makes the spacecraft thicker but not necessarily heavy. Another one, which is more interesting, is having an active way of shielding, which essentially boils down to detecting the particles maybe 100 meters, a kilometer away from the spacecraft, and having an electrostatic system to deflect it. Not magnetic, electrostatic. So you have essentially a particle coming through a capacitor, and all you need is this particle is extremely fast. Okay, so the amount of energy that you need to make a strong reflection is very high. You don't need to do that, okay, because you're going so fast. You only need a small reflection to make a picture. So you can design a system that is essentially a kind of warning system around the spacecraft as it travels that gets most of the high energy particles, just a mini tokens, okay, and deflect them out of the when the particle will be affected. There's not much you can do with gamma rays, okay. You can't have the gamma rays with electromagnetic system. So that's the realm of a passive protection for gamma rays. I'm not saying it's impossible. It's more work into
so that's the type of thing you're going to have to perfect before the Heterogeneous is going to be mine.
Well, the simple, straightforward approach is if you have enough energy on board, you can design the spacecraft to be thick enough to shield it. For example, if you're using hydrogen as a fuel, okay, you can surround yourself with tank, right? And it will be enough fuel that you have to have anyway, because you won't have some reserve and stuff like that. And once you get there, you don't need it anymore. You're done with the trip. You can get out of the spacecraft. The spacecraft will be surrounded by this tank or material that are absorbing radiation. But you don't want to put heavy metals and stuff like that. That's not good, obviously.
Why is hydrogen a good shield to use?
Hydrogen is a good shield because it's got one electron per nucleus, and so other atoms have for the same amount of mass, you have less electrons. Okay, so what happens is that you're looking at the properties of deflecting and absorbing the radiation is the interaction with the electrons in there. And it's high energy particles. The other energy particles are likely going to hit the electrons. Okay, and so if you have more electrons, it's better. Some people have been thinking about having nanotubes and capturing inside the nanotube, filling basically out of inside the nanotube. This way, you would actually be able to have a lot of hydrogen held by the nanotube particles. It's just that lot. Okay, you don't have to have a liquid hydrogen or tank that requires heavy maintenance. That's just some idea. I'm not going to include hydrogen. Anything that has hydrogen, like ammonia, for example, has a lot of hydrogen. It's a lot heavier, but it's just an engine that runs on hydrogen.
Any other questions? Thank our speaker. And also, next week, we're going to have Donna Stokes here from University of Houston, and she's going to be talking about structural and optical analysis of different types of superlattices. And it's going to be condensed matter physics. And also, this talk, like I said, should be on the web a little later. And so hopefully, if you get a chance to, you can check that out. And for students who are taking the